To divide radical expressions, we use three basic principles. One is the quotient rule for radicals. The quotient of nth roots equals the nth root of the quotient of the radicands. The second key principle is the definition of division. A divided by b equals the fraction a over b. We will also use the principle of equivalent fractions, both to reduce fractions and to create equivalent fractions by multiplying by a clever form of the number 1. Let's consider a few examples to simplify by a process known as rationalizing the denominator. In this process, we multiply a fraction by a clever 1 to eliminate any radical in the denominator of the fraction. To simplify 1 over root 5, we multiply by root 5 over root 5 to get root 5 over 5. To simplify x over 4 root 3, we multiply by root 3 over root 3 to get x root 3 over 12. Notice that in these two examples, we have multiplied the given fraction by a form of 1 that eliminates any radical in the denominator. We've chosen the form of 1 by cleverly exploiting the fact that the square root of a times the square root of a is the square root of a quantity squared, which equals a. In the third example, we need to multiply the denominator by something that produces the cube root of b cubed to eliminate the radical. We multiply the fraction by the cube root of b squared over the cube root of b squared. This produces the cube root of b cubed in the denominator, which simplifies to the b in the denominator. The previous examples bring up the question of when a radical is simplified. There are 4 conditions that indicate a radical is simplified. 1. There are no perfect powers that are factors of the radicand. This means that any radical factors of the form the nth root of x to the n have been simplified. 2. All exponents in the radicand are less than the index. 3. No radicand contains a fraction. And 4. No denominator contains a radical. We will repeatedly use the fact that the nth root of a to the n equals a for non-negative a. Let's simplify the expression the cube root of x over the cube root of 2y squared. We need a clever 1 to eliminate the radical in the denominator. What cube root should we choose? Since we ultimately need 2 cubed y cubed under the radical, we multiply by the cube root of 2 squared y over the cube root of 2 squared y. Next, we multiply fractions by multiplying numerators and multiplying denominators. Then, use the product rule for radicals in both the numerator and the denominator. Finally, we simplify the denominator to eliminate the radical. Once you become comfortable with these problems, it is very common to omit showing several steps. I will continue to emphasize every step in this video. Let's consider a different example with a binomial denominator. Simplify 13 over the quantity 4 plus root 3. Again, we need to determine what multiplier will eliminate the radical in the denominator. We need to get rid of the root 3 without introducing a radical factor to the 4. Using 4 minus root 3 over 4 minus root 3 will work because we can exploit the difference of squares formula in the denominator. First, we multiply the fractions. Then we want to simplify the numerator and the denominator. It turns out that leaving the numerator factored is best for any eventual simplification we might want to do. However, we need to expand the denominator to eliminate the radicals. We can FOIL in the denominator or recognize the difference of squares, but either way we get 4 squared minus root 3 squared in the denominator. This simplifies to 16 minus 3, or 13 in the denominator. We can cancel the factors of 13 in the numerator and denominator to get a simplified answer of 4 minus root 3. For the expression a plus b, the expression a minus b is called the conjugate. We frequently use the conjugate of a binomial denominator involving square roots when simplifying. Simplify 6 over the quantity root 5 minus root 2. Again, we need to eliminate the radicals in the denominator. We multiply by a clever 1 involving the conjugate of the denominator. Then we multiply fractions by multiplying numerators and multiplying denominators. Finally, we simplify the denominator by multiplication. It is useful to leave the numerator in factored forms in case some fraction simplification is possible. In this case, noticing that 6 equals 2 times 3 and 5 minus 2 is 3, we can cancel 3 from numerator and denominator. Our simplified answer is 2 times the quantity root 5 plus root 2, and we can either distribute the 2 or leave the answer in factored form. Let's look at one final example in which we have several operations involved. Simplify 4 root 2 minus 3 over root 8 plus root 32. There are a couple of issues facing us in this problem. We want to add radicals, so we will need like radicals, but we also have unsimplified radicals. Let's first simplify root 8 as 2 root 2 and root 32 as 4 root 2. We still have a denominator with a radical, so we multiply the middle term by a clever 1 of the form root 2 over root 2. Now we'll simplify the fraction by multiplying numerators and multiplying denominators. And we notice now that each term contains the radical root 2, so we can collect like terms. The easiest way to collect like terms in this case is to use the distributive law to factor out the common factor of root 2 and add the coefficients in parentheses. The coefficients in parentheses involve fractions, so we need common denominators to add fractions. Our final simplified answer is 29 square root of 2 over 4.